Thanks, Randy. All right, let's see if this all works. And so I am going to try and share my screen here. And let's get rid of that. Move that down there. Okay. Let's show. All right. Thank you very much. I'm delighted to be here in Kaga, and thank you very much, Mr. Mayor, for your wonderful introduction. I must say that this conference is much better organised than the ones in Australia. So fantastic job by Drone Japan and Randy and the whole group in organising this conference. So my talk today is going to be a systems update, which is really just an excuse to have a grab bag of all sorts of technologies that make sort of the lower levels of ArduPilot work and what's changed over the last 18 months. It's been about 18 months since the last conference that we held in Canberra. And just to start, I usually do give you an idea of the speed of development of ArduPilot. We've merged about 2,500 PRs roughly since the last conference. Over 8,000 patches, 420,000 lines of code have changed over the last 18 months. And we've had 314 individual contributors to just the main code base, which is fantastic. And many of those contributors are here in the audience. So thank you very much for contributing to ArduPilot. So the real theme of my talk today is connectivity and bridging. Basically, over the last 18 months, there's been a lot of work bringing all of the different types of buses that we support in ArduPilot and interconnecting them. And I've got a demonstration copter here. This is a little Hexoon Edu 450. And if you came up the front and saw it, you will see that it has a lot of additional pieces that aren't normally on a vehicle of this scale. It's demonstrating a lot of the new connectivity options. So there's been a lot of work on Ethernet connectivity for ArduPilot in the last 18 months. So the networking support has moved along a lot, and we're starting to see Ethernet being deployed in more vehicles. That's fantastic. We've now got virtual serial ports over both IPv4, so we have virtual serial ports over networking, and we have virtual serial ports over CAN as well, allowing us to transport all of our different serial protocols. We have DroneCan over Ethernet support. I'll be talking more about that later. IPv4 networking over serial, so bridging, so we get networking over fast serial ports. We have simulation linking virtual devices with real devices. And we now have RC input over CAN. So a lot of different transports bringing together. By the way, during this talk, feel free to ask questions during the talk if you want to shout out. Yes. So in this particular device I've got configured here is 12.5 megabits. The question from Tom was, he asked, with the IPv4 over serial, how fast is the serial link? So the typical serial link you set up with networking over serial is 12.5 megabit. So for reference, most of the CAN devices that are used by ArduPilot users are 1 megabit, which means we can actually get 12 times the bandwidth over a fast serial port than what we get over a direct CAN port with the normal BX CAN. You can, of course, configure our CAN ports for FD CAN at up to 8 megabit, but still the serial is actually a faster bus than what we can do over our CAN buses. And the device I've got here that I'll be showing in a minute is using a 12.5 megabit serial link doing PPP. So the virtual serial ports basically allow any of our ArduPilot serial protocols to be transported over IPv4 networking. So the most common use case is you have, for example, a virtual Mavlink TCP or UDP port. You can connect. So I've got the ground station I've got connected here. It might be hard to see. So I've got two connections here with Mav proxy to this little drone. One of them going via the here link using a 921 600 board here link air unit. And the second connection is a TCP connection going over Ethernet. So I've got an Ethernet connection. And so that's running into a serial to Ethernet adapter. So I get 12.5 megabit into the flight controller. The flight controller in this drone is a Cube Orange Plus, and the Cube Orange Plus does not have native Ethernet. But with the little adapter that I've got on here, you can get 12.5 megabit IPv4 networking into those H7-based flight controllers like Cube Orange Plus, and many other H7 flight controllers. So the other thing that has happened over the last 18 months is a lot of Lua bindings for networking. So now you can write Lua scripts that can access both local network resources. So with TCP/IP, talking to other Lua scripts, talking to other components like companion computers, to IP-based radios, to cameras. But you can also talk to internet resources. So you can have a Lua script that goes off and fetches data from the cloud. And that Lua script can be running directly on the flight controller, an STM32-based flight controller or a Linux-based flight controller, and it has access to internet resources while you're flying. And that offers a wealth of possibilities of what you can do inside your flight controller. One of the really useful cases I've had recently is talking to the CE thermal cameras like the ZT30, having a Lua script talking directly over UDP to a thermal camera and querying the thermal data from their cameras and then packaging that up as packets that are sent down to a ground station for geo-projections as part of a fire spotting project that I'm doing with the university with Peter and Michelle, who are here in the audience. But it just offers a huge possibilities for interacting with IP-based devices. And I think that over the coming years, we're going to see more and more aircraft using Ethernet IPv4 networking as the core backbone of the communication within the vehicle. Question. Yes, Tom again. Can you bootload? So the question was, can you bootload off it? Yes, indeed. We do have a IPv4 bootloader. So I might as well demonstrate that while I'm here. So here, if I go out of that, so this is a web page. It's a little hard to see because there's funny black bar I've got. So in this particular case, what I'm displaying, I'll just increase the font to make it a bit easier to read. So I've just connected to a web page. That web page is running directly on a small device. This small device here, and there's a couple of different available devices that there's this one here from QPilot, which is an amazingly small little Ethernet to serial and CAN adapter. I'll be passing this around in just a second. The one on here is the BoffBlox DroneNet device. It's got a little Ethernet 5-port Ethernet switch. Yep. Yes, difficult with the staying in camera view. All right. So, and there I'm talking to a web page that's running on that device. So that is a tiny web page, and there is a reboot for firmware update, and that goes to a network-based bootloader. So you can update firmware on devices across Ethernet. both your CAN peripherals can be updated over Ethernet from a remote ground station, and the firmware itself of these little devices can be updated over IPv4 networking, because we have a Ethernet-based bootloader on these devices. And while I'm here, might as well show. So this is a web server written in Lua. So you can write a complete web server in Lua if you want to. This is an extremely simple one. I know Tom has a much more sophisticated web server with lots of JavaScript and nice images, etc. I'm not much good at JavaScript, so I just did a very basic web server that runs on these little devices. And that web server, you can, for example, access your logs. So here I am accessing the logs on this device, and I can download those logs across from a ground station using an IP radio. So this, in fact, is coming via to a HereLink air unit. So I have a HereLink here, and I am connected to the HereLink from my laptop. That is going to the air unit on this drone. The air unit has an Ethernet connection that goes into the little Ethernet switch on this drone, and that goes into the Cube Orange Plus flight controller. So when I'm viewing these logs, that's utilizing the PPP serial to Ethernet connection and the Ethernet support in these devices to access logs sitting on the flight controller. And you can, in fact, download logs via this faster than you can get them on direct USB link. So it's faster to get the logs from your ground station remotely than it is to get the log by plugging in a USB cable. So it really is, you can get about 900 kilobytes a second, which is around twice as fast, roughly, than what you would get with a direct USB connection. Back to... All right. So, so I've already mentioned the network bootloader and the web server. And now at this stage, we really just have the fundamentals in place for this. What I'm expecting is that now it's really handing over to people who are better web developers to create better web interfaces. I know, for example, that Pete is going to be talking a bit about new JavaScript web-based interfaces. I would hope that we would be able to put that directly on the vehicle in future to be able to offer better, ground monitoring interfaces with the web server directly on the computer. And like I said, Tom has already developed such a one that he's working on with his drone. Okay, so these are the little serial to Ethernet devices. So these are AP periph based devices. So AP periph is our peripheral infrastructure for ArduPilot, which allows us to create GPSs and airspeed sensors and compasses and rangefinders and all the other different things that you might want as peripherals on your drone. What the networking has brought is peripherals that do Ethernet and IPv4 networking. And I'm just going to hand around just for people to have a look. So pass that around. I'd like it back at the end, but pass that around. So that little tiny device I've just started passing around is the CubePilot tiny ETH cube node device, which offers CAN bus and Ethernet and high-speed serial. And basically that little tiny device, you can plug that into your existing flight controller that doesn't have Ethernet, and you gain Ethernet on that device. And you also gain access to your CAN bus over Ethernet. And I'll be demonstrating that in just a second. Unfortunately, I only have one of the one on the right there on the screen is the BotBlocks DroneNet. The main difference with that one, it's a larger device that has a 5-port switch built in. And it's quite a smart switch, really marvelous device. That's what I'm using on this drone. And that 5-port switch means you can integrate a lot of devices, a lot of Ethernet devices to the vehicle, connect them into the flight controller, connect your gimbal, your IP radio, any other Ethernet-based devices can all be plugged in at once. And then you can access the monitoring of the switch in Lua. All right, so move on to the next one. So this one is quite recent. This is CAN over multicast UDP. So the point of this is now we've got Ethernet in ArduPilot. We need a suite of protocols to take advantage of the Ethernet. Obviously, there's the existing protocols like video streams, RTSP, there's the existing protocols for IP radios, but what we really wanted was a mature set of protocols that map to sensors and actuators and status of flying vehicles or submarines or rovers. And the obvious protocol was DroneCan. And so what this does is brings DroneCan to Ethernet or to IPv4 networking. And that means we get the full power of the DroneCan protocol with its hundreds of different messages and control mechanisms available on the IPv4 Ethernet network within the vehicle. This means, for example, that a companion computer, which has an Ethernet port, can see and control all of your CAN devices on your vehicle. So you can go and monitor the CAN traffic to all of your ESCs, your servos, your airspeed sensor. You can use it to update firmware. So Ethernet-based devices can fully participate in your DroneCan network. Because DroneCan is no longer limited to just CAN buses. It works on your Ethernet as well. So I'll just give a bit of a demonstration of that. So what I have here is, this is the DroneCan GUI tool. And so this is the DroneCan GUI tool. And I am connected to the you can see those ESCs. They'll be talking about these magic ESCs from Vim Drones in a second. So those DroneCan ESCs on the vehicle are connected to the flight controller over a CAN bus. That CAN bus is bridged onto the PPP link, the 12.5 megabit PPP link, which goes into that Ethernet switch. And that Ethernet switch is bridged across to the ground station, my laptop, across the network link that we have via HereLink and via, I've actually got a direct Ethernet cable as well to demonstrate that. So I've actually got pretending to be a companion computer. So I've got two links up, two Ethernet links or two network links up to the aircraft. And so I'm now seeing the status of these ESCs and I'm seeing streaming messages here. So I can go and tell it to go and run the motors, for example. And so that's now running a couple of motors here. I've got the wrong number in there. I put it in as 1. So that's now running the motors, controlled from the ground station and seeing all the telemetry from the ESCs coming down to the ground station with the DroneCan messages coming down across the Ethernet link, which is just sort of showing the types of capabilities that you can do. Now, it's got enough speed, I don't even need to enable the filtering. It'll happily bring the whole CAN bus over that link because we've got the 12.5 megabit serial, which easily carries the entire CAN bus. And I can switch to the other CAN bus. So, I could connect to a different, I won't bother now, but I could see the Here 4, which is on the other CAN bus, and connect to that. This really offers interesting possibilities for the ground station managing CAN devices, and I think particularly companion computers having access to all of the CAN devices across the Ethernet link. Any questions about any of that? Yes, George. Oh, I can repeat the question.
Fine, thanks. Is it going to be a good idea to link peripherals on board
UAV CAN peripherals on board with an Ethernet connection, or is a physical CAN bus still a better idea in this case?
So these devices, the control signals from the drone when it's flying are going directly over a physical CAN bus. The last slide of my talk, I'll be talking about future architectures for vehicles. And I suspect with larger vehicles that moving to an Ethernet-based backbone on large vehicles is going to be worthwhile. But I'll be talking more about that later. So the question from George was, is it better to use direct CAN bus for peripherals, or should we be going via Ethernet? So there's a bit more on that in a later slide. All right. So, okay. So you can also mix software in the loop with real CAN networks. So if I were to fire up a software in the loop simulation here of ArduPilot running your sim vehicle, running the simulation in Mission Planner, for example, then it would be able to see the ESCs and the GPS off the real vehicle, because those are projected onto the multicast UDP network over Ethernet. And that's the same network that SITL, the software in the loop simulator, uses. And this means you can develop CAN bus devices in SITL, and you can control those devices and have mixed simulation and physical devices mediated via this multicast UDP network. And I've found that incredibly useful. One of the things I've done with some users is when a remote user has an issue with a CAN bus device and I want to debug it, I get them to use our support system, support.ardupilot.org, to send all their telemetry to me in Australia. And I'll be showing more about support.ardupilot.org in a minute. That includes all of their CAN bus traffic coming via the support.ardupilot.org. And what I then do is I connect that incoming link from the user onto a local simulation, and I'm then able to interact with their remote CAN devices in a local simulation. So the physical devices are on another country coming from the other side of the world and appearing in my simulation locally, which means I can then test, so for example, if there is a CAN GPS that isn't behaving correctly, I can connect that remote CAN GPS to a local copy of SITL, and then I can edit the code, recompile and reconnect and see whether I've solved the problem, as though I was sitting in next to them wherever their physical device is. And it's an incredibly powerful technique to bridge the physical world to the simulated world. And that can be done remotely over a network from the other side of the world. We have a generic tool called DroneCan Bridge that comes as part of PyDroneCan that allows you to do N-way bridging across the different transports, because DroneCan supports CAN bus, of course, but it also supports SLCAN and MAVCAN and multicast UDP and TCP. You can bridge all of those together and create interesting networks where you combine devices. So I mentioned the support system, support.ardupilot.org. I'll just move this little window out of the way. So I know many of you already know about the ArduPilot support system. How many of you have used the ArduPilot support.ardupilot.org system? Maybe a third of you. How many of you have used it as a support engineer as opposed to a user? Yeah. So really, all of you should get yourself a support engineer ID to support people remotely. So if you haven't used it, I'd strongly suggest you go and have a look at support.ardupilot.org and read how it works. The usage since the last conference, the usage of support.ardupilot.org has gone up a lot. So I looked at the logs of the system, and we've had over 8,400 support sessions that have gone through the system since since we started the system, which was a bit before the last conference. And 195 million Mavlink packets have gone across the support system, which is quite a lot of Mavlink traffic. But it's really, there's a few partners who are using it a lot to support their users. And then a lot of other ArduPilot partners aren't taking advantage of it yet. So if you don't know about it, basically it's a way of, when you're trying to help one of your customers, you can get them to press this button, and you can see the button in the bottom right corner of that slide, which is the support proxy button in Mission Planner. And that connects their ground station to you as a support engineer, and you get a support engineer ID. So I can assign you an ID in the system, and that creates a secure connection between their computer and the support engineer. And then you can get all of their parameters, all of the telemetry, and you can view their CAN buses. You can actually look at the parameters on their CAN buses, and you can debug issues remotely. So it's a fantastically useful tool for supporting your end users. And if any of you don't have a support ID, please ask me about that, or ask on your partner support channel, and we can create a set of support engineer IDs for your company. All right. So in the continuing the grab bag of things we've been working on over the last year, we have a new HAL. It's actually a revival of a HAL we've had a number of years back called Hellquir. So, and Hellquir, so the Quirt, it runs on a lovely little flight controller called the Voxel 2. Have we got Eric? Yes, Eric up the back there. So we got Eric from Modal AI. And so Eric is been working with us very closely. It's been fantastic working with Eric because he understands the inside of Quirt and the Voxel 2 really well. So this little copter is a beautiful little vision-based development vehicle. It's as a test bed for the technologies they've got in Modal AI. And they've got a lovely visual odometry. In fact, they've got 2 visual odometry systems inside in the Modal AI system. And so we had this Quirt HAL a number of years back, and we've revived it now, and it's working very nicely. The picture in the bottom right is an example of skywriting. So what I did was I had this little drone flying outdoors, and it was flying purely on visual odometry. So it was flying with its camera and flying that skywriting. And so the green is the visual odometry path, and the red is what the GPS was saying. But it's actually not sure whether the GPS was more accurate or visual odometry, but it actually flies very nicely with a little visual odometry system. So it's an extremely compact little board, very powerful. So if you're after a vision-based vehicle and with visual odometry, it's well worth looking at the Voxel 2 system. Any questions about that at all? All right. So now I'll get on to my obsession at the moment. So I've had a real obsession in the last few months with this thing called Am32. So Am32 is an open source ESC firmware. It's been around for a few years, but it got a real boost when Beal Heli 32 stopped, shipping new firmware. And now a lot of ESC vendors are switching over to the Am32 open source firmware. And it really is a fantastic firmware. Massive credit, particularly to Alka and to Unit, the lead developers of Am32. Done a fantastic job in developing this firmware. So I've been thinking for a while, it would be fantastic if more people in the ArduPilot community could use an open source ESC firmware. And so that we can have a more intimate relationship between the flight controller and the ESC, and it's easier for us to debug ESC issues, because it's far too common to get issues with ESCs in ArduPilot-based vehicles. It's often very difficult to work out what is going wrong inside the ESC. So having an open source ESC where we can add additional debug information, where we can get really detailed internal information about what's happening in the ESC is a huge opportunity. So the AM32 is a very flexible design. At the moment, it supports 8 different microcontrollers. So there's STM32 and GD32 and AT32, and there's a RISC-V one that I've been working on, the CHV203, that will be merged soon into, I think, into AM32 main firmware. Of course, it supports things like D-Shot and BD-Shot and PWM inputs, and it supports EDT for extended D-Shot telemetry, giving you RPM and voltage and current. So that's the standard things, very similar to what you would get with BL-Heli, what you would have got with BL-Heli 32. But the really exciting thing about AM32 is because it's open source, we can extend it. And the big thing that we've done recently with extending it, I'll just move this window out of the way, is adding DroneCan support to AM32. So this vehicle here has a 4 AM32 DroneCan ESCs made by Bim Drones. So Wybeen, do you want to stand up and say hello? So this is Wybeen, the developer from Bim Drones, and I've been working very closely with him. He's another AM32 developer, and he's been creating AM32 DroneCan ESCs. And I'm going to pass some of these around the room so you can have a look, because they're really quite marvelous. I'll just tell you what I'm passing around. So I'm going to be passing around this development ESC. I've actually got the next slide, a picture of it there, the development ESC. And this is brilliant. So this is a little ESC. It's got a built-in motor. So there's a little tiny 4000 kV motor on there. And it's got CAN bus and debug ports all laid out on a little PCB. So for somebody as a software engineer, receiving this from Bim Drones, from Wybeen, was absolutely marvelous, because this enabled the development of DroneCan AM32. So I'm just going to pass those around, and I've also got, these are the nano ESCs, tiny little DroneCan AM32 ESCs made by Bim Drones that, so I'll pass some of these around, and so there you go. There's a tiny ESC, I would like to back at some point, but feel free to pass these around and have a look. They're very cool, very, very nice little ESCs. So, so what we've got is inside the firmware at the moment. We've only developed this firmware over the last month or two, but we have DroneCan parameter management. We have a full DroneCan bootloader for updating firmware. We have ESC telemetry. We have 4 different ESC designs that have been made already, and there's more on the way. I'm being contacted, almost every week, another vendor contacts me about wanting to create an AM32 ESC. I'm expecting that a lot of vendors will start making their own ESCs, because there's a reference design you can build against, and it's very, very easy to create a new ESC design that's perfect for your vehicle. So these are some of the ESCs so you can see there, the development ESC from Bim Drones on the left. The one in the top right, that's one from Sierra, and it's called the Sierra Pulse ESC. The one on the bottom right, that's a bit hard to see there, that's a Team Black Sheep 12S ESC. Now I only had a photo of the one without DroneCan, but there's a new version of that, which is based on the AT-F415 microcontroller. I've got a test version of it that is working with DroneCan, but it's a 90 amp 12S ESC that has full DroneCan support, which is marvelous to see a bit larger ESC coming out from a manufacturer like Team Black Sheep that has such a good reputation. Trappy, you're here somewhere in the audience, I believe. Yep, stand up and say hello. So we've got Trappy here from Team Black Sheep. So it's been marvelous working with TBS, and so they're going to be coming out with the DroneCan version of their Am32 ESC. And then the little tiny micro one, the nano one in the middle there is one of the ones I'm passing around. Question at the back there? So the question from Tim was whether telemetry works without DroneCan. Yes, so you get EDT telemetry over D-Shot. And so that ArduPilot supports that, the same as Am32. So you get RPM, voltage, current, and temperature, right? So basic telemetry you get with just the D-Shot, extended D-Shot telemetry support. With DroneCan, you can get a lot more data coming out. And so I'm expecting that at least for larger vehicles, most people would use DroneCan-based ESCs. All right, so I'd like to talk a bit about future ideas for DroneCan Am32 ESCs, because having the open source firmware gives us marvelous opportunities for doing more things with these ESCs. And what I would like to do is start having a more intimate relationship between the flight controller and the ESC, where you have a Lua script on the flight controller that sends messages to the ESC, changing the tuning of the ESC based on your phase of flight. And the most obvious case is where you've got a tilt rotor. So vehicles that have motors that are vertical when you're in hover and go to forward flight. And the optimal setting for an ESC is quite different in forward flight than it is in hover. So if you've got a long endurance drone, you want to get the most out of your ESCs, I want to be able to tell the ESC, I'm now in forward flight, change to this alternative parameter set, different advanced levels, turning off complementary PWM, changing the braking levels, changing the PWM frequencies while you're flying to get the optimal level for your particular vehicle. We could potentially do this in hover as well. If you're in a very quiescent state and you don't need very rapid control, you could adjust the ESC for maximum efficiency and then adjust it for maximum control when you need it, because it should be able to change very, very quickly, like in milliseconds, between the different configurations of the ESC. Now, this is all quite speculative. I haven't done much testing of this type of change, but I think it opens some interesting possibilities. So this is a new system that I've just added in the last week called FlexDebug. And this applies not just to Am32 ESCs, but to anyone making a DroneCan peripheral. And what this is a new DroneCan message that allows a peripheral to send arbitrary debug or internal data from the device to the flight controller and into a Lua script. And in the particular example I'm running on this vehicle, I've got the vehicle sending a data structure with a whole lot of internal information about what's happening inside the ESC, and I'm getting it to appear on the ground station. So I'll just go and show what's happening here. So somewhere here, yes. So if you have a look here, this is my MAV proxy console, and I'm going to reach in and have a look at this little graph here. So what I'm graphing here now is the commutation interval from inside the ESC. So if I actually start some of the motors, then you'll see that that is now showing in real time the commutation interval, and I'll need to start up the other motors and let's see. So, and we should start getting real-time telemetry. All right, so what that's doing is you can see it's streaming here. This is the little FlexDebug message. And the FlexDebug message is just a blob of data. It's sending a raw data structure from inside the ESC at whatever rate you want. In this case, I'm sending 25 Hertz, but it could be 200 Hertz. You're sending this raw debug data. And that debug data is available to a Lua script running on the flight controller. And that Lua script can log the data to our ArduPilot onboard bin logs, or it can, in this case, I'm sending it to the ground station as name value float, or you can make decisions about it. But the way the message works, I'll just stop those motors because that sound is annoying. So the message is extremely simple. This is the message here. So it's an extremely simple message. And what I've done is it's got a message ID where there's a reservation areas. So each vendor can reserve their own range of debug message IDs. So I'm expecting that many of the ArduPilot vendors that are developing their own peripherals, or vendors that are developing their own proprietary devices, proprietary ESCs. So I'm hoping that vendors like Hargrave and Currawong and others will add this message for sending rapid internal information from their devices and be able to log it within the ArduPilot flight controller. And this is trying to solve one of the core problems we've had with ESCs and servos. So I was talking yesterday to people from high tech. You can put their hands up, say hello. Yep. About the possibility of them sending this message from their servos to get internal debug information from their servos into the flight controller for logging and for down to the ground station. And I think this is going to be a marvelous way of debugging complex devices. All right. So nearly done. So this final slide. I'd like to talk a bit about sort of future architectures for ArduPilot. And the picture in the bottom right here, I'll just move this out of the way so you see that. That's Carbonics. Many thanks to Carbonics. Lakesh, you want to say hello? There's Lakesh. Thank you for allowing me to borrow this. I'm terrible at drawing, so I borrowed one of their pictures from their aircraft. So as aircraft get bigger and more complex, they've got more and more actuators, more and more devices. And the standard, most of those larger vehicles have been on CAN bus, moving to CAN bus over the last few years. One of the things that I think would be interesting to consider is whether over the next few years, vehicles like this start shifting to a Ethernet backbone with Ethernet to CAN adapters. These little devices, some of the ones I'm sending around, the QPilot one, for example, that tiny little device, it's an Ethernet to serial device, but it's also an Ethernet to CAN device. And it means that you can put those on the peripheries of your vehicle, have an Ethernet backbone, and then go out to CAN bus peripherals. Even better, I'd like to start seeing peripherals with native Ethernet support. I would love to add native Ethernet support to Am32 ESCs. So you actually plug an Ethernet cable directly into an ESC. And that offers interesting opportunities where we can use things like Ethernet link aggregation to allow you to have redundant Ethernet buses going around the vehicle. So if you lose one of the buses, the switches, the little switch built into this bot blocks Ethernet switch, the DroneNet device, is a very smart little switch. It can do things like link aggregation, which means when you've got multiple Ethernet buses around the vehicle and you lose one of those Ethernet buses, it automatically has the traffic on the other Ethernet bus, and instantaneously all of your traffic is still getting through. And I think that's going to be a marvelous way for larger vehicles over the next few years to have a really reliable high-speed backbone, which is universal for their video devices, IP radios, for all of the different types of devices, actuators, sensors, etc. So that's the end of my presentation. So questions at all before I wrap up and hand over to the next speaker? Tom.
One thing you mentioned is Lua can host web pages now.
Yes, indeed.
Yes. does that mean that on the autopilot itself, we could be running our own GCS?
Yes, you could indeed. Yes, we have all of the hooks necessary. So my talk today really presented all of the foundational pieces for what we could do, but what we haven't is developed the user interface layer for many of these pieces. Some of it's been improved a lot, like Hoi Bin from BIM Drones has really improved the DroneCan GUI tool recently. I'll just show you. So in here, for example, you'll notice that this interface, this ESC interface, you might not have seen before. It's got all of this telemetry information showing here directly in the ESC management tool. And if I go to the parameters, so these are the parameters on one of the Vim drones ESCs. So this is all of the internal tuning and control parameters for the little nano ESC running on the vehicle. And one of the things that Hoi Bin's done, we can actually, a little startup tune melody editor for editing the startup tune. So we need more of this sort of thing and making the better interfaces. We've got the fundamentals in place. We can create, Lua scripts can create complex web pages with JavaScript. We have server-side Lua support where embedded Lua scripts inside web HTML can access arbitrary Lua operations, parameters, etc. on the vehicle. So your web page running on your ground station, on your browser on the ground station, can access all of the hundreds and hundreds of Lua functions that are available within your flight controller, which offers enormous opportunities for creating really rich control environments for your vehicle. But we just need people who are good web developers to start taking advantage of that and develop nice interfaces. And hopefully in future talks, in future years, we'll be presenting some of those types of interfaces. Any other questions? All right, so thank you all very much. Deliberately finished just a little bit early. We were a little bit behind. And so we can, Randy, do you want to take a few minute break or should we go straight on to the next speaker? All right, so who's the next speaker? Alexander. So if you come up and start getting set up, and I wouldn't mind getting those various ESCs and bits of electronics back. If you could pass them towards the front, please, that would be greatly appreciated.